Hi everyone, welcome to another video for research design and analysis. This is the third in our series where we're talking about the central limit theorem and the sampling distribution of means. And in this video we want to talk about the calculation of z-scores and then how we can use those z-scores to calculate the probability of getting a certain sample mean. So as a reminder, right, we said that the central limit theorem states that regardless of whatever the parent distribution is, the sampling distribution of means will approximate a normal curve as the size of the sample gets larger and larger. And we said that normality in a statistical sense has a formal mathematical definition where if the mean, or that is to say the central tendency, and the standard deviation, which is to say the spread of the distribution are known, we can actually calculate the probability, right, through the probability density function. So these are all different normal curves, but our standard normal curve is the red distribution, where it has a mean of 0 and it has a standard deviation of 1. And under that standard normal distribution, right, we can plug those values into the formula for the normal curve, and then we can integrate the function to get, okay, what's the probability of getting a score between -1 and +1, or what's the probability of getting a score greater than 2? And really we can do this for any of these distributions, but I really want you to keep the standard normal distribution in mind because it's going to be really important when we talk about the calculation of these z-scores. So what are z-scores? Well, a z-score is a way of redescribing a particular x value with respect to the mean and the standard deviation. And to calculate it, you take the particular x value minus the mean and divide by the standard deviation. So in essence, a z-score tells you how far above or below the mean is a particular score in units of standard deviation. So we can solve this, right, for two different examples. Let's say we have a score of 15, but the mean is 10 and the standard deviation is 2.5, right? So a z-score in this case for a score of 15, we do 15 minus 10 divided by 2.5. That turns into 5 over 2.5. That is a z-score of 2 because the 15 is 2 standard deviations above the mean. Similarly, if we have a score of 130, the z-score there would be 130, and the mean in this example is 100, and the standard deviation is 15. So this would be 130 minus 100 over 15, which becomes 30 divided by 15, which is also 2. So although these scores look very different, right, 15 versus 130, they have the same z-score because in both cases, this score is 2 standard deviations above its mean. So z-scores give us a way of standardizing scores with respect to how far above or below the mean they are in units of standard deviation. And the nice thing about this then is if you do this for a set of scores, right, and you can take a whole bunch of x's, subtract off their mean and divide by the standard deviation, and what you'll end up with is a standard normal curve because the mean of the x's, right, minus the mean would be 0. If we had the true population mean minus the true population mean, it would be 0, right? And then 1 unit would be 1 standard deviation, 2 units would be 2 standard deviations. And so if we know the standard normal curve, right, and we can translate scores into z-scores, then we can say what is the probability of obtaining a score of that particular value or higher, right, that particular value or less, or obtaining scores between a particular range of scores. So the z-score transformation gives us a way of adapting any kind of set of data, any random variable, onto a normal curve. And then because we know the mathematical properties of the normal curve, we can integrate and solve for the area under the curve in a particular region and obtain the probability of getting that score. So let's think about our example from the previous video where we said how likely is it that you have a mean IQ of 100 or 3 or greater? And we said the answer is it depends on how big the sample is, right? And we said that again, IQ has a population mean of 100 and a population standard deviation of 15. So each of these sampling distributions then will have a standard error of 15 divided by the square root of the sample size. And we said, well, this clearly gives you 3 different sampling distributions, and therefore the probability of getting 103 or greater is going to change depending on whether or not your sample size was 25, whether it was 100, or whether it was 400. But now what we're going to do is take this a step further and not just say that it depends, but actually calculate the z-score under each one of these distributions and get the probability so we can say exactly how likely that is. So let's start with our first example. How likely is a sample mean IQ of 103 or greater when the sample size is 25? Well, again, our population mean is 100, our population standard deviation is 15, and in this example, the sample size is 25. Next, we need to solve for the z-score. So let's come down here. The z-score for 103, right? This definition of the z-score stays the same. We're taking a sample mean minus the population mean, but now we have to be careful because the standard deviation that we divide by is actually the standard error, right? Because we don't want the standard deviation of scores, we want the standard deviation of sample means. So we're not just going to divide by 15, but instead we're going to divide by 15 divided by the square root of 5, which is 15 over 5, which is 3, right? So again, we're using the standard deviation of this sampling distribution, which is what we call the standard error. But the standard error is really just a type of standard deviation, right? But the key thing here is we want to know about a sample mean relative to the population mean, so we use the standard deviation of sample means. If we wanted this to just be scores, right, what's the probability of getting a person with an IQ of 103, we would just use the population values. But here we're asking about a sample, so we're going to use that standard error in the denominator, and that works out to be a z-score of 1. So now on a standard normal curve, because we know the mathematical definition of that probability density function, we can say what is the area under the curve beyond 1 standard deviation, and it turns out that that's about 16%. So about 16% of the time you would expect to get a sample mean of 103 or greater if your sample size was 25. Changing that around now, right now let's think about a sample of 100 on this green distribution. The population mean and standard deviation stay the same, but our n is now 100. And that's going to actually change the z-score because our definition of the z-score does not change, and the numerator does not change because we're still asking about 103 minus 100, but the standard deviation here changes because the standard error of the mean when our sample size is 100 is 15 divided by the square root of 100, which is 1.5, which gives us an overall z-score of 2.0. So this is a more extreme value because we're now 2 standard deviations above the mean, and you can see that in turn that has an effect on shrinking the probability. Under the blue distribution, about 16% of the sample means were greater than 103, but under the green distribution, only about 2% of the sample means are greater than 103. So now, in the final example, let's think about what happens when we do this with a sample of 400 people. Again, our population mean and standard deviation stay the same, so the numerator of our z-score calculation is the same, but now the denominator again is getting smaller because we're dividing by the standard error, which is 15 divided by the square root of 400, which works out to be 0.75, which gives us a z-score of 4. So now we're saying this is an even more extreme deviation, right, when we have 400 individuals in the sample. Because under this red sampling distribution of means, right, every 0.75 point increase is a standard deviation. So we are 4 standard deviations above the mean now. And what's the probability of getting a z-score greater than or equal to 4? And it works out to be less than 0.001%. So this is very unlikely to happen to get a sample mean of 103 or greater if our sample size was 400, right? So we can see the probability of this shrinking as we increase our sample size. When our sample size was 25, about 16% of sample means were greater than 103. When our sample size was 100, about 2% of the means were greater than 103. And now when our sample size is 400, less than 1% of the means are greater than 103. So the probability of observing a particular mean depends a lot on the sample size because of the effect that's going to have on the standard error of the mean. We can also apply the same logic now if rather than saying, well, what's the probability of getting a score above or below a certain value, we can actually put confidence intervals around particular values. So we could, for instance, say what values of the mean would occur about 95% of the time. Well, on our standard normal curve, 95% of the values fall between negative 1.96 and positive 1.96. So negative 1.96 separates the bottom 2.5% of the distribution from the top 97.5%. Positive 1.96 separates the top 2.5% of the distribution from the bottom 97.5%. And if we're shaving 2.5% off here and we're shaving 2.5% off here, that means in the middle, we're left with 95%. So between plus and minus 1.96 is the middle 95% of the distribution. So this same window is always going to apply on a normal curve. If we want to turn it back into original units though, all we need to do is multiply 1.96 by the standard deviation and then add that or subtract it from the mean in order to turn that back into individual scores. So we can see some examples of this on the following slides, but the main thing to think about, right, is that 1.96 is the standard benchmark on the normal curve. If we scale that by the standard deviation, right, we might be multiplying 1.96 by a big number here, or we might be multiplying it by a small number. So it ultimately comes down to how big or large is this standard deviation, and that's going to determine the upper and lower limits of our 95% confidence interval around the mean. So let's consider our three different examples again. And we're going to say now, rather than what's the probability of getting 103 or higher, we're going to say what values of the mean would occur 95% of the time. And remember that we're going to have a particular z-score, which separates the most extreme 5% of the scores from the middle 95% of the scores, and that's 1.96. But the trick is, how do we get from 1.96 back to the actual values, right? So we have this critical z-score that we're going to use, but we'd really like to know what the upper and lower limits are in terms of the original units. So we have to rearrange our formula a little bit in order to solve for the upper and lower limits. So in our first example, we had an n of 25, and that led to a standard error of the mean of 3. Because remember, our standard deviation for intelligence tests is 15, and 15 divided by the square root of 25 is 3, so the standard error of the mean in this example is 3. Now, we know on the standard normal curve that 1.96 is the z-score that separates the middlemost 95% of the distribution. So we also know that the population mu is 100 and the standard error of the mean should be 3. So what we need to do in these situations is solve for x, because that will give us the score that is 1.96 standard deviations above the mean and 1.96 standard deviations below the mean. So working with negative 1.96 first, we can calculate the lower limit by taking the mean, right? And through algebraic rearrangement of our z-score function, we're going to do minus 1.96 times 3, and that works out to be 94.12. For the upper limit, we do the same thing, right? We rearrange that fraction in order to solve for x bar, and that's going to tell us the upper limit in terms of raw scores, and the upper limit in terms of means is 100 plus 1.96 times 3, which works out to be 105.88. So in our example, right, where we have a mean of 100 and a population standard deviation of 15, if we're taking samples of n equals 25, 95% of our sample means should fall between our lower limit of 94.12 and our upper limit of 105.88, because these are both within 1.96 standard errors of the true population mean, and therefore 95% of sample means will fall between them. We can do the same calculation now, again, changing our sample size, right? So the critical z-score does not change. It's still 1.96 that separates the middle 95% of the distribution from the extreme 5%. But now the standard error of our mean is going to be different because our sample size is different. So now the n is 100. The standard error of the mean is going to be 15 divided by the square root of 100, which is 1.5. And then we can rearrange our z-score formula to solve for the mean value that gives us that critical 2.5 percentile and 97.5 percentile, right? But rather than percentiles, we want actual scores. So we're going to turn that into a lower limit, which works out to be 100 minus 1.96 times 1.5, so that's 97.06, and an upper limit, which is 100 plus 1.96 times 1.5, which is 102.94. And we can see that a little more easily, right, if we actually plot these values on the sampling distribution itself. But when n is equal to 100, our sample distribution gets tighter, and we can now see that 95% of sample means are going to fall between 97%, or sorry, between a score of 97 and between a score of 102.9. So 95% of sample means will fall within 1.96 standard errors still, but the definition of a standard error has changed because our sample has gotten bigger. Okay, one final example. Let's do it with our biggest sample size, just to again demonstrate what this formula actually is, right, and the effect that the size of the sample has on the spread of the sample distribution. So again, our critical z-score is going to be 1.96 because that always separates the middle 95% of the distribution on the standard normal curve. But now that we have an n of 400, the standard error of the mean for us is going to be 0.75 because again, the standard deviation is 15, so the standard error will be 15 divided by the square root of 400, which is 0.75. And again, we know what the critical z-score is, and we know what mu and the standard error are, so what we need to do is algebraically rearrange this in order to solve for the particular sample mean values that give us a lower limit and an upper limit. And working with 1.96 first will give us the lower limit, and that's 100 minus 1.96 times 1.5, right, is 98.5. Our upper limit uses positive 1.96, right, times 1.5, and that works out to be 101.47. Again, drawing this on the actual sampling distribution probably makes it a little more clear, but our mean is 100, and when we're taking samples of size 400, the standard error gets an awful lot tighter. So now you can see our distribution is a lot narrower. 95% of the distribution still falls within 1.96 standard errors to the left and 1.96 standard errors to the right. But to actually convert those critical z-scores into units, we need to multiply by the standard error and then subtract it or add it to the mean. And we end up with a lower limit of 98.5 and an upper limit of 101.47. 95% of sample means are going to fall in that range. So in this video, we've talked about calculating a 95% confidence interval. And I want you to take a second to think about which one is going to be wider, because we can actually calculate confidence intervals for any percentage that we want. But for now, let's consider three: a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. So this, again, the 95% confidence interval separates the middle 95% from the extreme 5%. A 90% confidence interval similarly would separate the middle 90% from the extreme 10%. And a 99% confidence interval is going to separate the middle 99% from the extreme 1%. So take a minute to think about these questions. You can go ahead and pause the video until you've got your answers and then go ahead and start it up again. But which do you think is going to be wider? A 95% confidence interval or a 90% confidence interval? And then a 95% confidence interval or a 99% confidence interval. Go ahead and pause the video and generate your answer and then start it up again. So the answer is that a 95% confidence interval is going to be wider than a 90% confidence interval, and a 99% confidence interval is going to be wider than a 95% confidence interval. Right? And hopefully that's the answer that you came to, but you can think about it in these terms. Each of these is separating the middle part of a distribution from the extreme tails. So we started with the 95% confidence interval, and it was separating the middle 95% from the extreme 5%, putting 2.5% in each tail. The 90% confidence interval is going to separate the middle 90% from the extreme 10%, right? So it's actually putting 5% in each tail. So that means that the 90% confidence interval is going to be narrower than the 95% confidence interval. Similarly, the 99% confidence interval separates the middle 99% of the distribution from the extreme 1%. So it's only putting 0.5% in each tail. So that 99% confidence interval is going to be even wider than the 95% confidence interval, because essentially it's going to capture more of the sample means. And as we increase the size of that confidence interval, it's going to get wider and wider because it's ensuring greater and greater capture of what's happening due to sampling variability.